CMOS easing chips from PCIe cards to applications.
So yeah, thanks for the kind introduction. I'm Chris Kim. I'm a faculty at the University of Minnesota. My background is maybe a little bit different from most of you guys. I'm a chip designer by training. What that means is I work with foundries like TSMC, get their PDK, design their circuits, send the database to them. 3 months later, they'll give us packaged chips, and yield is almost, I don't know, 100%. So that's kind of what I'm used to. I come from the fabless foundry world. So I'm kind of an outsider. So kudos to the organizers though for inviting me, someone like me who had no prior training on optimization. But I'm delighted to be here and kind of, I mean, I love the fact that there's new ideas, new perspectives that are coming together. So I'll kind of walk you through our journey. So we've been designing these Ising solver chips in CMOS technology. So everything is foundry based. As you can see from the title, from PCIe cards to applications, that's where we are in this journey. We have PCIe cards with Ising chips running 24/7, trying to solve these problems. And then we just launched a company called COBI. It stands for Coupled Oscillator Based Intelligence. Just to inflict some pain and frustration in my life. So it's been an interesting experience. So the first few slides are going to be non-technical. I'll just show you what we're building, and then we'll kind of go into a little bit more depth in terms of the chip design. So this captures what we're after. And this is one of the actual, a chip that we prototyped a few years ago. So this, you can see the piece of silicon here next to a tip of a pencil. So you can see the scale difference, how tiny these things are. We can integrate 4 quantum-inspired annealers. So each core would be equivalent to a, say, 60 all-to-all connected Ising chip. And each core consumes about 10 milliwatts of power. So that's 0.01 watts of power. So you can have 1,000 of these. The power will be 10 watts. Okay, I mean, I didn't do anything special. It's really the foundry and CMOS that kind of delivers that kind of performance, density, energy savings, and so on. So this is what we're building. This is the abstract view of the chip. So each core has about 50 to 60 all-to-all connected oscillators. So each node is an oscillator. Sometimes I kind of call them qubits. Yeah, this is the configuration. Of course, there's nothing stopping us from building a giant all-to-all connected hardware because everything is modular. Again, we're not reinventing anything. We're using everything that the ecosystem CMOS has built, has delivered so far. So, I mean, there's nothing stopping us from taping out a chip that's all-to-all connected with a lot more spins. However, we're realizing there's a right size for everything, right? So the cores are already pretty big. And the analogy I use is it's kind of seeing like a school bus parked in my driveway. It kind of looks odd because it's huge from a chip design perspective. So there's a right size, optimal size for everything. Just like CPUs, you don't have a 1,000-bit CPU, you have a 64-bit one, right? So this is what our chip has. We're not reinventing the manufacturing paradigm. everything is based on a foundry process. All the software you use is based on the chip design EDA software. So that's how we achieve this economy of scale. This is our latest prototype. It's a PCIe card. So it's like just like a graphics card. You plug in to your Linux box. Our chips are actually these in the middle. So 8 of those on a single card. Everything else is off the shelf. For example, this big chip is, I mean, you can read, it's an FPGA chip. All it's doing right now is just communication. So it supports the PCIe stack. And then some voltage regulator ICs here. Okay, so it's pretty much you plug it in, install a driver that was custom made. We have a C++ software and then a Python wrapper on top of that. So that's what we have. And then this is actually a low resolution image of a Linux box with the PCIe card with 4 daughter cards. And then you have a couple more in the background. And those are slots used for SSDs. If you want to buy extra SSDs and plug it in, I mean, you plug it in the back. But we kind of use all the slots there. And just a quick video here. And these are, yeah, thanks to D-Wave and all the pioneering work they've done with the open source software, we can leverage all that. So this is running some standard Ising problem. I think this is, let me stop. Right now it's 500 spin problems. So these are actually, you decompose, send each subproblem to the chip, and then get the solution back and you somehow stitch them together. And of course, you can dial up and down the global search post-processing if you want a more accurate solution. But I mean, you can see, since we have 6 cards, you can kick off multiple problems. We can bump it up to 2,500 spins. It gets running. So you can see all the, I mean, it's actually running on the hardware. You can kick off a whole bunch of them. They're running in parallel. You get the solutions back, as you can see here. Yeah. So that's kind of what we're building. And then to the real outline. So quantum versus quantum inspired. I think many of you are familiar, but just kind of to recap. And then how did we build this 59 spin all-to-all connected Ising solver chip? And then some chip testing results. These are just characterization results, not application results. So these are just random max cut graphs and looking at the success probability. Some results from these small or tiny problems that you can fit in a single chip, so MIS and 3SAT. And then slightly less small problems. It's not large in the grand scheme of things, but it's 2,500 spins. At least that's a good place to start. And then really the conclusions, the learnings, and yeah, the next steps. Yeah, so very promising technology, quantum, fascinating. And all the good ideas come from talking to people in the emerging technology domain. So really kind of helps people like me kind of think outside the box. So yeah, and a lot of private investment, public investment as well. I mean, this is a few years old, so I mean, there's a lot more companies that started since then. Startups and also large organizations investing in this technology, but a lot of challenges as well, as we all know. The cooling aspect, the shielding, and the radiation protection from radiation sources, vibration, noise, all the extra circuitry that has to go in, the microwave circuits, analog chips that have to work under cryogenic conditions, the large form factor, limited scalability, very expensive, and it's just a high risk. So we're borrowing only the kind of the properties of quantum that actually help us get the solution faster at low energy compared to digital, without the baggage of quantum, such as the cooling and the interface circuits. So the two properties we're borrowing is basically superposition and entanglement, and we're emulating these in using classical oscillators. Superposition, as we know, it's a 0 and 1 state intermingle, and then you kind of, when it comes to reading out the state, you can threshold it, call it a 0 or 1. So we're using oscillators as our qubits to emulate qubits, as you can see on the right-hand side here. So you have the top oscillator, bottom oscillator. If the oscillator is free running, the phase is moving around. It's just random. Okay? It's not tight or synchronized with anything. So it's an analog property, but you can have some basis function and kind of visualize it in some rotating vector. Now, if you have two of those and you connect a resistor between, say, two nodes, there's energy transfer between the two. So the phase of one oscillator pulls or pushes the phase of the other oscillator, and it's done in a mutual way. So they eventually, if you wait long enough, they lock into each other. You can configure it in a diagonal fashion, you get a negative coupling. So that's kind of emulating these quantum properties. By no means this is actual quantum, but it's just emulating quantum. And you can simulate these using like a SPICE simulator. 3 oscillators coupled in whatever configuration, you can verify that the phases are moving around accordingly. And then, so once you kind of switch to the classical world, you can just start implementing in a foundry technology. These are all kind of well understood circuits. It's simple oscillator loop of inverting gates. And we're not even using sinusoidal oscillators, because sinusoidal linear circuits they're not very scalable. If you kind of give up the linearity, and just use a square wave, then you can actually have very dense, high performance circuits. Okay? So that's what we did. So just a quick high level comparison. Most of the parameters are very equivalent. So we can focus on what we built here. It's a 59 oscillator, all-to-all coupled oscillator system. Connectivity is 58, so it's natively all-to-all. That brings down the number of couplers to 1,700. Weight resolution about 5-bit. But really the advantage is the power. Okay? So it's 0.01 watt power. If it was anything higher than that, I would be concerned. It's just transistors, right? CMOS. That's why CMOS is the dominant technology. Everything based on, manufacturing is done by TSMC. And then, of course, by no means CMOS is the only oscillator you can use. There's the superconducting device approach, the coherent Ising machine approach. You can do spintronic, MTJs, some phase change devices. You have the CMOS and even some mechanical oscillator. So any oscillator would get the job done. We just have to use the one with the highest integration density, lowest energy, highest speed. Right? So if anything can be done by CMOS, it will be done by CMOS, as the saying goes. And then some other reasons why CMOS seems to be the way to go. The industry itself, it's on track to hit $1 trillion by 2030. So, and it's a healthy, the compound annual growth rate is, double digits, right? So it's a high-tech, industry, a lot of growth, only accelerated by, further by AI. That's what enables these, chips with some ridiculous number of transistors, like tens of billions of transistors. It's such an important technology that, there's a lot of tension, geopolitical tension, and try to secure the supply chain. There's still heavy, enormous amount of investment, right? The EUV devices. Last time I checked, it was $200 million per machine. Now it's second generation, third generation, 300 million dollars per machine. A lot of the, we heard about the coherent Ising machine. A lot of heavy lifting is actually done by the FPGA chip. So, and FPGA chips, as far as I remember, all CMOS based. And then the other thing, when you hear about oscillator chips or, oscillating this and that, it's a little bit misleading in that if you actually try to build a chip and implement it, the oscillator is almost, very small, right? It's tiny. Everything else is, okay, you program the coupler, you measure the phase. Yeah, so it's all like classical circuits, like logic gates and flip-flops, right? So you need some kind of technologies that actually can provide all the supporting circuitry. Okay, so we've been taping out like crazy. We're part of this, DARPA project where the goal is to build these Ising, these optimization engines. So every month or two, we have a new tape out. And because why do we need so many chips? Because emulating quantum in a classical technology, that's easier said than done. If you just do all-to-all coupled, connect one point to another, it just becomes a pile of spaghetti, right? So you have to do it in a very coordinated way. So there's some kind of, pretty detailed engineering effort that needs to go into this. And then you have to feed the learnings to the next generation design, and you have to iterate that. So we've been on this kind of crazy schedule for the past couple of years. And this is a PCIe card, M.2 PCIe card. 4 of these are going to one PCIe card, but you can see what it looks like. So now we're kind of at a point where we really have to tackle real applications, and that's where the frustration starts. But so the big picture, I'm sure we are all aware. You start with a huge combinatorial optimization problems, oftentimes, tens of thousands of spins or more. But you have to break it up into little pieces so that you can actually fit it in the hardware. And that's no different from any kind of compute flow. Like you can have a huge GPU, but your neural net model is always going to be much, much larger than a single GPU. So you always have that kind of decomposing step. You just don't call it decomposing, but you do have that baked into the algorithm. The beauty of this approach is the nature just gives you the ground state or something close to the ground state. You do have to clean it up, and that's a design, choice of the application, software. And then you kind of iterate this loop over and over again until you get a good enough solution. And the applications we heard are kind of across the board. Although, there's once you add constraints and other requirements, it quickly becomes intractable to solve. Okay, so let's talk about our actual design. So we focus on connectivity because the more connectivity I can provide as a chip designer, less work you need, embedding that problem onto the hardware. So these are some architectures out there: King's Graph, IBM proprietary, architecture, all the D-Wave, architectures. This is Chimera is a little bit old, but yeah, still. And then our architecture. So like I said, right now we're at 60 or 58 connectivity of 58 5-bit resolution coupling. How did we achieve that? So I'll talk a little bit about that. So this is what our earlier chip looks like. This is like 2 or 3 years old, so it's kind of history, ancient right now, but it was done in the 65 nanometer technology. The die size is 2 millimeters by 2.4 millimeters. This chip had 1 core, so it doesn't have 4 cores. And here we have, it's basically a crossbar array. I'll give you the actual architecture in the next slide, but it's a crossbar array, meaning that's how you get all the oscillators talk to all the other oscillators. And then the design is very modular. The only block we really have to focus on is that single coupler cell. But the oscillator and the coupler and everything is designed in that such that when you just tile it using a script, everything becomes a massively connected all-to-all architecture. Yeah, we have a couple, so we don't utilize all 63 oscillators as spins. We keep a couple of them for show. So that's kind of the injection locking mechanism that kind of binarizes the phases better. We wanted to test that. A couple of oscillators are used for calibration. So you don't have oscillators there, you have calibration cells there. So that leaves us with 59 spins. Yeah, power consumption, 0.01 watts. The oscillation frequency in this chip was about 5 megahertz, which is very slow if you think about CPU speeds in the gigahertz range. But I mean, it's pretty straightforward why it has to be 5 megahertz, because you need all the oscillators talking to all the other oscillators with a 5-bit resolution. So if you add the stage delays one by one, it comes out to be about 5 megahertz. Our latest designs in more advanced technologies, this number is about 40 megahertz. So with scaling, we do get the benefit, yeah, speed up. Everything is room temperature. It's just a chip on a board. And this is the older setup where it's not a PCIe card. It's just printed circuit board plugged into a mini computer. So how do we achieve all-to-all connectivity and uniformity? Right? You can't just have a pile of spaghetti hoping everything is uniform. So yeah, the key idea is we have this crossbar array, and we have loops here in the horizontal direction and vertical direction. So you have oscillators everywhere, basically, vertical, horizontal. But we kind of tie 2 oscillators together. They form like a single super oscillator, but it's a cross shape. And then every location in this array, there's one pair and another pair kind of intersecting each other. So that's where you put those coupler cells. So this gives us a very uniform structure. So like I said, you just design one of these cells and just tile it. And then you get this all-to-all connected architecture. The circuit also is a little bit different. We are doing analog computing, but not in the voltage or current or some capacitive coupling. We just do everything in the time domain. Because time is something we have good control over, even though the voltage might be extremely low. And that makes our design very scalable. So yeah, there's an architecture kind of idea, also the circuit idea as well. And I mean, nothing really special here. This is the adjacency matrix. So basically, you start from the end user application, decompose it, somehow extract all the weights, and then this goes onto the chip. And then chip starts the oscillation, settles to the ground state, you read out the phases, it sends it back. And that flight time is in the order of, I mean, it depends on the technology, but 10 microseconds or something. And we're leveraging PCIe in all the high-speed communication, so we didn't have to reinvent any of that. So let's take a look at some of the characterization results. And these charts were inspired by a lot of the work from the CI coherent Ising machine papers and D-Wave papers. So x-axis, these are all random graph results, by the way. So x-axis is the graph density. Y-axis is the success probability, with the criterion being 99% of the best software, best Hamiltonian found by software. So 99%, that was our target. And then you have a bunch of results here. So you have the red and orange way up there, in terms of success probability, and then the other two down here. So that's before and after the post-processing. So you can do a little bit of cleanup by kind of flipping each spin, see if there's a better solution within a Hamming distance of 1. That can be, and that's all done inside the chip. So that's, again, the power of CMOS. If there's some function or feature you want to add, you want to accelerate, you can offload that to the chip. You can design the chip that does that for you, rather than pulling the data out and doing that all in Python. So we're kind of seeing more and more of those CPU features kind of going into the chip. So the chip itself is very hybrid. It's a coupled oscillator array, but with a lot of digital functions supporting that. So that's kind of, so with, as you see, with that kind of simple post-processing, you can kind of improve the success probability by, say, an order of magnitude. So it's definitely worth it. That overhead is like 5% in terms of energy. So it's definitely worth doing that. We also have the shill knob, the injection locking knob, where you can pulse the oscillators with 2 times their fundamental frequency. So it kind of locks them into odd or even phases. So you can see the results, no shill versus shill. So, I mean, I don't know, red seems to be slightly better than orange, right? On average, if you look at the whole thing. So there's some marginal improvement there. It's not a game changer by any means, but it kind of helps a little bit. It's more pronounced for if you compare the green versus blue. But since we're going to do post-processing anyways, we have to look at, compare orange versus red. So these are some of the results. So the main takeaway here is for a single sample, we can get about 10% probability, success probability for this 99% criterion. Now we can kind of tune the knobs we have. So shill is also part of that adjacency matrix. So we can adjust the amount of shill, no shill, weak shill, strong shill, medium shill. It's all digitally programmable. So you can see, I mean, yeah, so there's kind of a right amount of shill. It's the, like the Goldilocks theorem. There's kind of an optimal amount of shill you can inject and at least kind of get the highest success probability. And as you'll notice, that flattens that curve, right? The low density graph, it was struggling. Now it's kind of flat. Right? We also have a calibration knob. So all the oscillators are individually calibratable. So you can calibrate the frequencies one by one, trying to get them to lock more easily. Again, marginal improvement, red versus orange after post-processing. So not sure if it's worth it, because calibration does require a lot of time. We can't do it exhaustively because you have 60 oscillators and 5-bit resolution. You can't do that exhaustively, so you have to use some greedy approach. So this is by no means the optimal way of calibrating, but it does improve things a little bit. We also looked at the impact of initial phase. So you can have all the oscillators start from 0 phase and let them lock, or you can kind of randomize them, the initial phase, by letting them oscillate for a while and then kind of turn on the weights. And that's something within your control. So if you look at starting random versus uniform initial phase, random is slightly better. However, if you think about it, how do you randomize the initial phase? You have to let them run for a while, and then you can start solving, right? So you lose precious computation time just randomizing the phase. So in the end, we kind of dropped the random initial phase because it doubles the computation time, for example. Yeah, so I mean, these are choices one can make. So those are the characterization results. And then in terms of power, we measure the power for different graph densities. Like I said, for the densest graph, it's about 10 milliwatts. So the question is, what's the energy? You need to know the number of cycles you want to wait until it settles down. So 250. Of course, we've run all these sweep tests to see what that number should be. And then how many solutions do you want to sample until you give up, right? The more you sample, you get better solutions. So say 20. So if you plug in those numbers and compare the results with, say, a CPU solving a single sub-problem, you can calculate the speed up and energy savings. So speed up is rather modest, but this is comparing our 65 nanometer, chip, COBI chip versus 14 nanometer Intel CPU. But speed up, we still are getting a speed up about 2x, but it's really the energy savings. Okay, and if you can get 700x or 1000x energy savings, you can run 1,000 of these in parallel with the same power budget. Yeah, so that's kind of the fun part for me, all the chip design and getting it to work. Now the frustrating part, tackling real problems. So we started with tiny problems. I should have probably called it tiny, not small, but so meaning problems I can fit in my core, okay, without having to decompose a problem. So we're comparing ourselves against the quantum computers, the Rydberg array, the science paper, some of the D-Wave papers, and then also algorithms, taboo search, simulated annealing. So yeah, it's a busy chart, but if you just look at the first column, x-axis is the time to solution, y-axis is the energy to solution. Okay, so you want to be in the lower left corner. The quantum approaches tend to be way up there simply because of the cooling, okay, the overhead. The software-based approaches are sort of in the middle. But the caveat here is it's still at the sub-problem level, right? A problem that you can fit on our hardware. Once you have to decompose it, I mean, then that overhead needs to be accounted for. So this is just looking at the core, the core level performance. And we've tried it on 3 classes of problems, the planar MIS, because those problem sets are available from the science paper, SAT problem, something that you can fit in a chip, which limits us to like 10 to 11 variables, even with the most compact formulation, SAT formulations out there. And then non-planar MIS. Since our architecture is all-to-all, we can map any MIS, so we can go up to 51 spins. Why not 59 and 51? Because for the local field, you have to merge some of those local fields to provide that dynamic range. Yeah, so here we couldn't compare with the existing quantum computers, but just us versus software. So this is kind of how things stack up. I mean, we tried a wide variety of problems with planted solutions and or some problem sets we could download. So I mean, that's why we have a range of success probabilities. But this is how things stack up at the moment. And now on to the slightly larger problem. So 2500 spin, I showed you the video demo earlier. They have these problems have about an 8-bit weight resolution. So even though our hardware can only support 5 bits, we can still solve 8-bit resolution problems with near 100% accuracy. Yeah, so this is for one such problem. We do have results on a lot of these problem instances, but this is just for one example. What we tried here is x-axis is the amount of global search or post-processing. Yes, sure, almost done. So x-axis is the amount of global search, meaning that you decompose, solve a problem, and you kind of stitch all the solutions together, get one global solution, but using that as a seed and running global tableau search on it. So you can kind of completely get, have no global post-processing, or you can kind of, dial it up and have a lot more search. So it's kind of, this is hybrid, right? So obviously, the more global search you apply, the computation time just goes up because CPU has to do more work. But you can see the accuracy, the blue line there. So it holds up until we completely turn off the global search, right? So by applying some modest amount of global search, you can kind of get a pretty competitive solution. I mean, near 100%. So these are some results we're getting. Yeah, so this kind of indicates that a lot of the problems that need to find a pretty, pristine solution, you do need to, have some global search. Otherwise, it's too approximate. And this is just looking at the time to the solution. Really, always keep in mind the energy to solution is far lower than any CPU-based approach. Yeah, so that concludes this talk. Really, the state of the art, the technology to beat is heuristic-based algorithms. And these heuristic-based algorithms have been developed for decades, right? So it's hard for something to come in and then just kind of say, okay, we can outperform everything that has been done. Yeah, these Ising solvers can be manufactured in today's foundry process. These are the most advanced, most stable technology on this planet. So that's why we use them for all our electronics. But the QUBO challenges, and this is kind of preaching to the choir, but what are the applications, right? If you try to kind of map some application, traveling salesman or what have you, that's been around for decades, like SAT problems. Yeah, not sure if that's the right application for our hardware. The problem formulation, very tricky, like we heard all day today. The number of spins, you have to manage that. Constraints, the customers are very demanding in terms of constraints, and these often involve higher order interactions. We've looked into 3-body, 4-body interactions, very against nature. So I'm not sure if there's a solution that's waiting to be discovered. The other thing is QUBO, as the problem size grows, the file size for storing the weights, and this is a practical kind of challenge, but it tends to get huge, gigabytes of QUBO weights. So there's a memory bottleneck as well. From an ASIC chip design point of view, we're trying to bring more of these features into the chip. So pre-processing, post-processing. Right now, we have an FPGA doing the PCIe that will eventually come into the chip, DDR eventually into the chip. I think the opportunity, and this has not been discussed extensively today, is the opportunity for massively parallel operation. So even with 1,000 cores, the power that we need consumed is only 10 watts. So if we kind of bring that energy down to 0, and we can have, say, 1 million cores on a laptop, will that be enough, right, for us to this whole community to make an impact? So so hopefully the answer is yes, but we'll have to see. And the hybrid aspect, the mixing and matching the global search with our analog hardware. These are some of the challenges going forward. Yeah, thank you.
Thank you for the interesting talk. Are there any questions?
Very interesting talk. Thank you very much. Maybe I missed it, but how do you program the magnitude and the sign of the interactions in this implementation?
Yeah, we have memory cells. So if I can go back. Yeah, this unit cell, this contains, memory cells. So we just write into those memory cells. That becomes the weight. So whatever 5-bit weight, that integer number that we had in the adjacency table, it goes in here.
But what's actually happening? You had a diagram with your ring oscillators connected by a resistor or something quite early on.
Right, right. So that resistor, yeah, that resistor is just kind of to help understand what's going on. It's not a resistor. It's those weights are controlling the delay, the push-pull of the signal edges in some weighted fashion. So that weight affects the control signal, which affects the push-pull of the phases. So it's kind of doing what a resistor would do, but using these gates. And that's the secret sauce that allows you to really scale and make this dense. Because resistors are not available in CMOS chips. Yeah.
And how do you change the sign of that?
Oh, sign of that. Everything is in the logic. Yeah. So there's some logic there. So there's a sign bit, obviously. There's a 5-bit. 1 bit is the sign bit, and that sign bit is used to kind of control these in some fashion.
I appreciate that secret sauce, but maybe we can talk offline a bit about that.
Yeah.
Thanks.
Thanks a lot for the talk. It was very, very interesting. I had a question. So you said that you could do the post-processing of bit strings by design on the chip. Could you expand a bit on that? Give us details a bit of, and how far can you go in the post-processing in the design of the chip?
Anything you can think of that can be, like, okay, take a sample, I'm going to flip bits. It's all becomes a state machine. So anything you can imagine, it's worth putting in, it can be done. And everything is written in Verilog, hardware description language, like a C program. So you kind of click cycle by cycle to verify everything is working. So that's how we build these, GPU chips, right? You have the full end-to-end verification flow. So if you verify your design to the fine details, when the silicon comes back, it's just going to behave the way you verified it. Yeah. So there's nothing, there's no secret there. It's just how chips are built. Yeah. It's just digital.
Thanks a lot. And also just a question. So how do you let the system evolve to get to the ground state of the Hamiltonian, but how do you make sure that it's not just in a local minima and then how does it escape? How do you?
Yeah, so it is what it is, basically nature. So, but we have full control over how many cycles you want to wait until a sample. It's all kind of a synchronized system. So if when you program the adjacency matrix, actually there's a control register. Sample every 213 cycles. It will count 213 cycles and sample it. How do we get out of the local minima? You can play with the weights or the shell or initial state. Those are the knobs available. But at the end of the day, what matters is whether we can solve 100,000 spin problems, right? But once you get to that level, all this kind of fine little details you do, you forget about it. Depending on how you formulate it, you get a lot, the results were a lot more than, tuning the shill, for example.
All right, thanks a lot.
Are there other questions from the audience?
So I have a question on the technology node of your chip. So you use a 28 nanometer. That is FinFET technology? FinFET?
No,
planar?
not FinFET. It's right before FinFET.
Ah,
So
okay. I see.
design rules
I
are
see.
very similar to
I
FinFET.
see.
It's very restrictive.
So then what is the best technology node for your Ising, CMOS based Ising machine? Are there any idea about
Yeah,
that?
we don't have a choice as a chip designer. Foundry
Yes.
in Taiwan, they
Ah,
call the shots.
I see. Mhm.
If they're going to go to 3 nanometer,
mhm.
we just have to go there.
Ah, I see.
So, I mean,
It
we
doesn't matter.
cannot
Mhm.
stop,
Mhm. Okay.
right? Because we have a lot of digital and memory and
Yes.
a lot of PCIe and DDR,
Mhm.
right? So we have to just keep up.
I see.
So we're going from, I mean, this is kind of old, 65, then 28.
Mhm.
We successfully migrated. We just have to keep following all the way to the end.
Okay,
More
I
stuff.
see.
And that's been our kind of guiding
Mhm.
principle. If there's an optimal node, then you're dead on arrival.
Okay.
I mean, it's not competitive. Yeah.
Okay, I got it. Thank you.
Any other questions from the audience? If not, I have a question. Why limited to 5 bits precision?
It's a trade-off. If you want 6 bits, you have to give up half the spins because everything costs.
Okay.
It's a resource allocation problem. So
Okay.
if we can go to 1 bit, I can give you, a lot more spins. Yeah, 300 spins. Yeah. And we've even thought of that direction, but I think you want some resolution. Yeah.
Well, if there are no more questions, okay, you have a question. Constantine?
Yeah, just to add to the question Helmut asked, what about weights that you put in the adjacency matrix in the diagonal? Because I saw it was always the same term.
Yeah.
Is there a way to tune that too?
That's dummy actually, because the diagonal is where you kind of tie the two vertical horizontal together. So it doesn't matter what you program. It's a slightly different cell that goes into the diagonal. It just makes sure the two oscillators are just locked, not even locked, tied together. Yeah. I mean, it's not physically tied together. So of course, everything is based on whatever the foundry provides, inverters, NANDs, and NORs. But that dummy, the diagonal is a dummy. Yeah, basically.
Okay, thanks.
All right, then let's thank the speakers from the last session and all the speakers of the day.